going to cover our submission to the SPEE 2024 Software Symposium, a bake-off for DCA autocasting. For the bake-off, we used the latest version of our Analytics for Energy Forecasting and Valuations workflow, which is pure Spotfire, no robots, no trips to the cloud. Everything is run off of a Python data function library, which is attached to the DXP. So pure Spotfire. For the submitted bake-off test, it was run on Spotfire 1414 on a Dell XPS 7590. It had 8 cores and 16 logical processors, 32 gig of RAM, and a terabyte SSD running Windows 11. The timing of the MCMC DCA Autocast of 1022 wells worked out at 5.6 wells per second, both streams. And for the MCMC Markov Chain Monte Carlo EUR of 1022 wells, averaged out at 3.4 wells per second, both streams. Subsequent to the test, I upgraded my Dell laptop to an XPS 16 9640 Ultra 9 running at 25 megahertz. It had 16 cores and 22 logical processors, 64 gig of RAM, and a 4 terabyte SSD, again running under Windows 11. Rerunning the bake-off test on this machine gave me an MCMC DCA Autocast for the 1022 wells. I was getting 23.8 wells per second, both streams. And the MCMC EUR of 1022 wells was 4.3 wells per second, both streams. Well, let's get to it then. Step 1, looking at the data canvas. The well header data and monthly production data CSV were loaded as is. The only Spotfire transformation added through the data canvas on both inputs was to change the long integer XL, those API data types, to string for compatibility with the template. Step 2. On the Connect data page, columns from the well header and monthly production data were mapped into the template. In reality, only the lats and longs from the header were only used for the maps in the template. Only the monthly production data was used for the DCA Autocast. Step 3. Looking at the map and the data, it was clear that the data was grouped over multiple basins. As our Autocast uses only production date and rates, I chose to run all basins with the same Autocast parameters. On the Select Wells page, all 1022 wells were marked and selected for the well set. Step 4. On the Review Production Date page, it was noted that the minimum number of production months was 7. Some wells had only monthly gas data. The days on value seemed to be filled for all records, which is normally not the case. When days on is null, we assume 30.4 days to calculate the per day rate. Step 5. All the production wells were marked and the new well set was initialized for the Autocast. Step 6. Setting the Autocast parameters. For the initial Autocast run, the minimum records for production was set to 6 so that all wells would be forecast. The high-low thresholds for oil were set to 2 and -2, and for gas 3 and -3 respectively. Step 7. Running the Autocast. The DCA MCMC Autocast ran in 3 minutes for the 1022 wells, both streams, which equates to 5.67 wells per second. From the ratio plot, it was observed that the gas stream high-low thresholds were not activating the final segment detection. A review of the curves confirmed this. The MCMC diagnostics indicated that the sample burn-in of 1200 was more than sufficient to stabilize the parameters QI, DI effective, the B factor for each well in the well set. Parameter time is undetermined, which is expected. Step 8. I went back and tuned the Autocast parameters and reran the DCA Autocast. For the second run, the high-low thresholds were tightened. Oil was set to 1.5 and minus 1.5 and the gas 2 and minus 2 respectively. DCA Autocast timing was as before at 5.67 wells per second, both streams. The MCMC EUR run was run to see the distribution of EURs for the well set. This process is compute heavy and took 5 minutes to complete for the 1022 wells, approximately 3.4 wells per second, both streams. Step 9. The forecast curves were reviewed and the forecast data exported to Excel for submission to the SPEE. What did we learn from the SPEE Software Symposium and feedback on the submissions? In terms of Autocast speed and accuracy, we did pretty well. I chose to Autocast all the wells with the same parameters, but could have tuned the parameters for each basin to improve the forecast result. We knew that time was poorly defined, and our Autocast EURs were on the pessimistic side for this reason. Our previous hour Autocast DCA code used a final decline parameter, and we will revert to that approach soon. Percentage error is the recommended approach by the SPEE. I'm pleased to announce that the implementation of the final decline and percentage error to our MCMC DCA Autocast is in the latest A4E release, and has improved the forecast quality, especially at the tail. Congratulations to all who participated in the event. I'm sure that we all learned and gathered ideas as to how to improve these automated forecast tools.